We're now going to look at how to find maxima and minima using Lagrange multipliers. The method of Lagrange multipliers. So example number 1, suppose a manufacturing company budgeted $80,000 per month for labor and capital. The monthly output in units of objects made from the company is f of x, y of 4xy minus 8x, where x thousands is spent on labor and y $1,000 is spent on capital every month. How should the $80,000 be allocated to labor and capital to maximize monthly output? So we want to maximize f of xy is equal to f of xy minus 8x, subject to x plus y equal to 80. This is the constraint equation. Set the constraint equation equal to 0 so that x plus y minus 80 equals 0. The left-hand side of the equation is the constraint equation called g, and g of xy is equal to x plus y minus 80. The idea behind Lagrange multipliers is to create a new function, capital F of x, y, lambda, which is equal to little f of x, y, plus lambda times g of x, y. And you just need to find out what lambda is. Let's formalize this with some theory. Theorem. Any local extrema of z is equal to little f of x, y, subject to any constraint g of x, y equal to 0, will be any x0, y0, such that the partial derivative of capital F with respect to x of x, y, lambda equals 0. The partial derivative of capital F with respect to y of x, y, lambda equals 0. And the partial derivative of capital F sub lambda of x, y, lambda equals 0, where capital F of x, y, lambda is equal to little f of x, y plus lambda g of x, y. The process of Lagrange multipliers is to set up capital F of x, y, lambda and find x, y, lambda so that the first partial derivatives with respect to all three are 0. Then evaluate f of x, y at each of the critical points, and the largest function value is the maximum, and the smallest is the minimum. So let's do a continuation of example 1. Let x equal the amount spent on labor. Let y equal the amount spent on capital. Little f of xy is equal to the output. Want to maximize little f of xy is equal to 4xy minus 8x, subject to g of xy is equal to x plus y minus 80. Now, let's set up f of xy lambda, capital F of xy lambda. Capital F of xy lambda will equal little f of xy plus lambda times g of xy. Well, that will equal 4xy minus 8x plus lambda times x plus y minus 80. Now find the partial derivatives of capital F of x, y, lambda with respect to x, y, and lambda. So the partial derivative of capital F with respect to x is going to equal 4y minus 8 plus lambda. Capital F partial derivative with respect to y is going to equal 4x plus lambda. And the partial derivative of capital F with respect to lambda is going to equal x plus y minus 80. Now set all three partial derivatives equal to 0. So the partial derivative of f with respect capital F with respect to x is equal to 4y minus 8 plus lambda equals 0. Capital F partial derivative with respect to y is equal to 4x plus lambda equals 0. And capital F with respect to lambda is equal to x plus y minus 80 equals 0. Y is equal to 2 minus lambda over 4 when you solve the first equation for y. Solve the second equation for x, you get x is equal to minus lambda over 4. And now substitute those two into the third equation. So you have minus lambda over 4 plus 2 minus lambda over 4 minus 80 equals 0. That simplifies to minus lambda over 2 minus 78 equals 0. So minus lambda over 2 is equal to 78. And lambda is equal to negative 156. That means that x is equal to minus 156 over 4, which is equal to 39. And y is equal to 2 minus negative 156 over 4, which is equal to 41. This means the critical point is 3941. Now evaluate the input value at all the critical points. The largest value is the maximum, and the smallest value is the minimum. Since this only has one critical point, then the output function evaluated at this point, which is f, little f, of 3941, is equal to 4 times 39 times 41 minus 8 times 39 is equal to 6,084 is the maximum output. This means the maximum output of 6,084 units occurs when 39,000 of labor and $41,000 of capital are used. Example number 2. Find the maximum and minimum of f of xy is equal to x squared minus y squared, subject to g of xy is equal to is equal to x squared plus y squared minus 25 equals 0. First, find f, capital F, of xy lambda, which is equal to little f of xy plus lambda times g of xy. So that's going to equal x squared minus y squared plus lambda times x squared plus y squared minus 25. Now find the partial derivatives with respect to x, y, and lambda and set them equal to 0. So the partial derivative of capital F with respect to x is 2x plus 2x lambda equals 0. The partial derivative of capital F with respect to y is minus 2y plus 2y lambda equal to 0. And the partial derivative of f with capital F with respect to lambda is x squared plus y squared minus 25 equals 0. Let's factor the top two equations. You can pull a 2x and get 1 plus lambda equals 0. And you take 2x plus 2x lambda equals 0. take negative 2y plus 2y lambda, you will get, that factors as 2y times minus 1 plus lambda equal to 0. This says that x equals 0 and lambda equals negative 1 from the top first equation. Second equation says y equals 0 and lambda equals 1. The last equation is x squared plus y squared equals 25. If x equals 0 and lambda equals negative 1, then the last equation becomes 0 squared plus y squared equals 25. That says y is equal to plus or minus 5. And the critical points for lambda equal to negative 1 are 0, 5, and 0, negative 5. If y equals 0, then lambda equals 1. And the last equation becomes x squared plus 0 squared is equal to 25. So x is equal to plus or minus 5. And the critical points for lambda equals 1 are 5, 0, and negative 5, 0. Now evaluate f of xy, which is equal to x squared minus y squared, little f of xy that is, at all 4 critical points. So f of 0, 5 will be 0 squared minus 5 squared is equal to negative 25. F of 0, negative 5 will be 0 squared minus a negative 5 squared equals negative 25. F of 5, 0 is going to be 5 squared minus 0 squared is equal to 25. And f of negative 5, 0 is equal to negative 5 squared minus 0 squared is equal to 25. The maximum value is 25. It occurs at 5, 0 and negative 5, 0. And the minimum value is negative 25 and is occurring at 0, 5 and 0, negative 5. One more example, example number 3. The Cobb-Douglas production function is used in economics to model production levels based on labor and equipment. Suppose we have a specific Cobb-Douglas function of the form little f of xy is equal to 50, x to the 0.4, y to the 0.6, where x is the dollar amount spent on labor and y is the dollar amount spent on equipment. Use the method of Lagrange multipliers to determine how much should be spent on labor and how much should be spent on equipment to maximize productivity if we have a total of $1.5 billion to invest in labor and equipment. So x is equal to the number of dollars of labor, and y is equal to the number of dollars of equipment. F of xy is your productivity. We want to maximize f of xy equal to 50, x to the 0.4, y to the 0.6. subject to x plus y is equal to 1.5 million. X plus y minus 1.5 equals 0. So g of xy is equal to x plus y minus 1.5. Capital F of xy lambda is going to equal 50 times x to the 0.4, y to the 0.6, plus lambda times x plus y minus 1.5. Now find the partial derivatives with respect to x, y, and lambda and set equal to 0. So the partial derivative of capital F with respect to x will be negative 20, x to the negative 0.6, y to the 0.6, plus lambda equal to 0. The partial derivative of f with capital F with respect to y is going to equal 30 x to the 0.4 and y to the negative 0.4 plus lambda equal to 0. And capital F's partial derivative with respect to lambda is going to equal x plus y minus 1.5 equal to 0. Notice the first two equations can be solved for lambda in this case. Lambda for the first equation is equal to minus 20 x to the negative 0.6, y to the 0.6. And the second equation says that lambda is equal to negative 30 x to the 0.4, y to the negative 0.4. Lambda must equal itself, so set these two expressions equal to each other. So minus 20 x to the negative 0.6, y to the 0.6 is equal to negative 30 x to the 0.4, y to the negative 0.4. Notice, now divide both sides by x to the negative 0.6 and y to the negative 0.4 to clear the negative exponents. So we have negative 20 x to the negative 0.6, y to the 0.6 divided by x to the negative 0.6, y to the negative 0.4 is equal to negative 30 x to the 0.4, y to the negative 0.4 divided by x to the negative 0.6, y to the negative 0.4. And then we're going to simplify and get y by itself. This gives y is equal to 3/2 x. Now use the last equation to find the critical points. The last equation was x plus y minus 1.5 equals 0. So x plus 3/2 x minus 1.5 equals 0. That gives me 5/2 x is equal to positive 1.5. So productivity is max. Oh, and that says that x is equal to 1. Sorry. And so y is equal to 3/2 times x, or 3/2 times 1 is equal to 1.5. So productivity is maximized when $1 million of labor and $1.5 million of equipment are used and give a productivity of F of 1.5, which is equal to 50 times 1 to the 0.4, 1.5 to the 0.6 is equal to 63.8 units.